Hi everyone, welcome to the frequency domain. In this episode, we are going to design a fifth order elliptic low-pass filter using high-low impedance lines. We are going to start by reviewing the filter properties. Then we will introduce the equivalent lump element circuit model of the filter. Next, we will see how we can use high-low impedance lines to design a low-pass filter. And finally, we are going to use the ADS software to develop the layout. Generally, elliptic filters can have sharper response in compared to Chebyshev filters. So, same as before, we are going to design a filter with 10 GHz 3 dB bandwidth, 0.1 dB passband ripple, but this time with 40 dB loss at 14 GHz. The two equivalent lumped element circuit models for elliptic filter all look like this. For both circuits at zero frequency, you can find a short circuit path between input and output. And as the frequency is increased, this path is gone. In this design, we are going to use the second form. There is no solid equation to set the order of an elliptic filter, like something we have used with Chebyshev filters. But there are some tables that you can set the order of your filter based on them. What you need to know in order to use these tables is that how much loss you need at a specific frequency in the stop band region. And this frequency is normalized with respect to cutoff frequency. So in our design, it's 40 dB loss at omega s equals to 1.4, which results in a fifth order filter. So this is our filter equivalent circuit with its corresponding element values. Using high-low impedance microstrip lines to implement an elliptic filter is exactly like a stepped impedance filter. It means that a low impedance line translates into a capacitor and a high impedance line to an inductor. In order to do that, there are a few things that we have to know. The low and high impedance values should be lower and higher than the system impedance. As the ratio of the high to low impedances are increased, we are going to have a better filter. For low impedance lines, we are limited by the consuming area. That's because as you lowering the impedance of a line, its width is increased. In contrast, for high impedance lines, it's the PCB fabrication process that's going to stop us to reach higher impedances. So let's see what does it mean when we are working with a substrate. We are going to use the line calc of the ADS software and RO4003C with the thickness of 0.508 mm as the substrate. For high impedance line, we are going to use a line with the width of 0.2 mm, which has a corresponding impedance of around 110 ohms. And for low impedance line, a 4 mm wide line results in an impedance of 20 ohms. We also need to know the corresponding wavelengths for high and low impedance lines. It is needed to calculate the length of each section. There are two equations in Mr. Poser book which you can use to calculate the length of each section. If we apply them for our filter, these values are extracted. And this is how the layout of our filter looks like in a microstrip form. Thank you all for watching this video. As always, we hope that you find the video useful. And we also appreciate it if you share your thoughts about the video in the comment section. If you like the video, please don't forget to hit the like button. And you're welcome to subscribe to the channel for more videos. See you next time.